Welcome everybody to this special online class. This is the last of the classes that we need to do in order to make up the time that we lost due to the canceled classes due to snowpocalypse. So today we're going to be taking a look at Chapter 6, and this is now when the textbook catches up to how we've been doing it correctly in class, where finally we're going to be doing hypothesis tests with means of samples. And this is the last chapter that we need to take a look at before we will get into the hypothesis tests that are done every day in psychology. So we're getting to the point where there will be no more special cases, no more special assumptions. We'll get down to the real life work that a psychologist will do. So just to remind you where we're going, once again, to give that example of the educational psychologist, if you're working with, say, a sample of 14 autistic children, and you're trying to test a treatment, an educational intervention to help with their learning outcomes, when that experiment is done without the skills that we're working on right now, all you could say is that your treatment either works or doesn't work for those 14 individuals. What we want to get to the point, and what hypothesis testing is all about, is to be able to take our data from these 14 individuals and then responsibly, ethically, intelligently say whether or not that treatment will generalize to the population of students or whether it won't generalize. So this expands psychology's reach beyond the subjects that we're working with so that we can help not just tens of individuals, but hundreds of thousands, millions of individuals, thus expanding the power of psychology. So that's what we're working towards. The really cool stuff that we're able to do, the hypothesis testing, taking a look at actual real life psychology data, and using the same tools that a professional psychologist will do, our statistical ninjas in psychology would do in order to analyze their real data, develop those real world skills. And as we've seen previously, we have a 5-step hypothesis testing procedure. And up until now, you have been getting ready to the point where you can do the entire process alone. So that's what we're working towards. And right at this point, out of those 5 steps, you now completely are able to do step number 1. You can make the research and null hypothesis for both a two-tailed and a one-tailed test. You are completely ready for and completely able to do step number 3. You can now look up the critical zones, the critical values, the lines in the sand for both a one-tailed and a two-tailed test. Step number 4 can completely do that. You can now calculate the z-score for your sample on that comparison distribution. And then step number 5, you can make that decision whether to accept or reject the null hypothesis. The only thing that you're missing right now is step number 2. How can you determine that comparison distribution? And today is the day where we are going to fill in that knowledge. We're going to develop that skill so that you can do step number 2, and you will now have the complete set of skills required in order to do a hypothesis test from start to finish, all on your own. All right, so today we're going to revisit one more time the idea of samples and populations, and then we're going to talk about that comparison distribution, which we've already learned about. So that comparison distribution is that distribution of sample means, and we've already introduced it, we've already talked about it, and today we're just going to be very explicit on how to determine those characteristics, what the central limit theorem tells us about calculating the mean of that distribution of sample means and calculating the standard deviation. So we need those two pieces of information, the mean and the standard deviation of that distribution of sample means, in order to determine the characteristics of our comparison distribution. So as I mentioned before, out of the 5 steps, you know, step 1, 3, 4, and 5, you can do those all on your own at this point. So what we're doing now is we're filling in that final piece of information, step number 2. So all those times that I promised you that we're going to see how to do this in the next chapter, this is the next chapter. Chapter 6 has come. And it used to be needed to be given to you, but now you're going to get to develop the skills so that you yourself can calculate that mean and that standard deviation for your comparison distribution. All right, so here we go. So just as a brief refresher, this all ties into, this idea of a comparison distribution ties into the idea of samples and populations. So this concept that we've looked at before comes back again, and the idea that samples are used to estimate population parameters, that you take the mean of a sample in order to predict the population mean, that again comes into play. And that has, as you've seen, been the basis for the logic behind hypothesis testing. Importantly for our purposes is the idea that from an unknown population, so we're working towards now the idea that we don't know the population parameters, we don't know what the mean is, we don't know what the standard deviation is, much more realistic situation for a psychologist to find themselves in. But what we can do is we can take a sample from that population. And that sample, even though we know it comes from the population, because we don't know anything about the population, it's a mystery where that sample came from. So even though we can measure the mean and the standard deviation of the sample, we don't know where from the population it came from. We don't know if it came from, for example, the center of the population, or if it came from the bottom extreme of the population. So again, even though we can measure that mean and that standard deviation, we don't know if it's from the bottom extreme of the population because we don't know the population. And we also don't know if it came from the upper extreme of the population, once again, because we don't know that population. So we're going to see how we're going to work with what we know. We're going to work with that sample. But importantly, the idea is that these samples all come from the same population. And you can lift many different samples from that same population. It all depends upon where they come from. And as we saw before, this idea of taking samples from a population leads to the idea of that distribution of sample means. So once again, you take samples from a population, calculate their means. This sample over here has a sample mean. This sample over here has a different sample mean. They both come from the same population. And if we do this over and over and over again, we can create a distribution of sample means, a collection of all the possible sample means from every possible random sample of a particular size. And going forward, this idea of a particular size is going to become very important. So this distribution of sample means is always the idea of a distribution for a sample of a particular size. So for example, a distribution of sample means for a size of 5. So you have 5 individuals, like we do in this example, in every single sample. You could have a completely different distribution of sample means if you increase your sample size to 10. And then you would have a completely different distribution of sample means if you then increase your sample size to 20. So that distribution of sample means is always tied to that sample size. So it always has to be a distribution of means from samples, all of which have the same size. They all come from different parts of the distribution, different parts of the population, but they all have exactly the same sample size. Different sample means, same sample size. And as we saw before, this is a very important point to remember going forward. As we saw before with our look at the population of die rolls and the distribution of sample means for those die rolls, the distribution of sample means has the same shape and is the same distribution as a population distribution, only for a sample size of 1. So this is that example where the distribution of sample means matches the population distribution. So this flat uniform distribution, that is the distribution, the population distribution for all dice rolls. This is the distribution of sample means for a sample size of 1, a single dice roll. And this is the only case, the only situation where your distribution of sample means is the same as your population distribution. And this is a very, very important point to get across, because up until now your textbook has been playing fast and loose with, oh, we have a sample size of 1. compare it to the population distribution. We have a sample size of 1, compare it to the population distribution. We have a single subject, compare it to the population distribution. So up until now, you have become very practiced at taking your single data point, taking your single individual, your single subject, and comparing it to the population distribution. Now we have to change that. Now we have to do it correctly, because now we are no longer taking a single individual, a single subject. We're going to take a group of subjects. And the reason that you're able to compare a single subject to the population mean is because you are supposed to compare it to the population the distribution of sample means. But in this and only this case, the distribution of sample means and the population distribution are the same. So you were able to do that up until now because you were dealing with a sample size of 1, a single subject, a single individual. But as soon as you go to a sample size greater than 1, that distribution of sample means no longer looks like your population distribution. And you are no longer allowed to compare your sample mean to the population distribution. And the way that I like to remember this is that it is unfair to compare your group of individuals, your sample of individuals, to a distribution of single people. It's unfair to compare your group to a distribution of individuals. It's unfair to compare your sample to a distribution of individuals. You need to compare your sample to a distribution of samples. You need to compare your sample mean to a distribution of sample means. So just bear that in mind. We are no longer comparing anything to the population distribution. Going forward, always compare your sample mean to that distribution of sample means. And as we saw before, when your sample mean is when your sample is a size of 2, this is what your distribution of sample means looks like. For example, for dice rolls, sample size of 3, that distribution of sample means changes. So this is that idea of your distribution of sample means is tied directly to the size of your sample. Sample size of 4, that distribution of sample means changes again. Sample size of 5, that distribution of sample means changes once more. And if we kept playing this game, sample size of 6, 7, 8, 9, 10, 20, 30, whatever your sample size, your distribution of sample means changes its shape depending upon the size of your sample. So remember that going forward, because that's going to be important for our future hypothesis testing. So this would be the way to come up with a distribution of sample means, to simply take every possible sample from a population, calculate its mean, and then out of all of those means, figure out the distribution of sample means. However, even though this is theoretically possible, practically it's not possible. We usually only have access to one sample, the sample that we studied, the sample that we tested, the sample in our experiment. So in this case, how do we figure out the distribution of sample means? Well, what we do is we use what we know about how these distributions are formed, and we use what we know about the relation between the population distribution and the distribution of sample means. So how do we determine this? Determining the characteristics. Well, we go back to the central limit theorem. So we go back to that little bit of mathemagic that allows all of psychology and all of inferential statistics to occur. So the central limit theorem says that for any population with a mean of mu and a standard deviation of sigma, so this is really any population. This is your population distribution. You have a population distribution of individuals that has a mean of mu and a standard deviation of sigma. For that population, the distribution of sample means for a sample size of n, so whatever size you choose, if you have a sample size of 10, this will work. If you have a sample size of 20, this will work. If you have a sample size of 482, this will work. The distribution of sample means from a sample size of a certain size, sample size of n, will have a mean of mu. It'll have the same mean as your population distribution, your distribution of sample means, your comparison distribution will have the same mean as your population distribution, but the standard deviation of your distribution of sample means, the standard deviation of your comparison distribution will have a deviation that is equal to the standard deviation of the population divided by the square root of the size of your sample. And that is the important part. That divided by the square root of the sample is the part you need to remember. That's the new little bit. That's the part that if you're going to make an error here, you're going to forget that. So when you're doing your characteristics of a distribution of sample means, when you're calculating your comparison distribution, make sure that at some point you are dividing the standard deviation of the population by the square root of the size of your sample. If you don't take the square root at some point, you're doing something wrong, you're missing a step. So bear that in mind. That's the crucial step where if students make an error, that's the part that they miss. All right, and then the last little part here is that distribution of sample means, that comparison distribution, will approach a normal distribution as the size of your sample approaches infinity. And what that part means is that regardless of the shape of your population, you know that your distribution of sample means, your comparison distribution, will have a normal distribution, and that opens up the appendix and allows us to do hypothesis testing using that unit normal distribution table. So once again, just to drive this home, we have a population distribution. So let's say that this is your population distribution of individuals. Your distribution of sample means will look the same when your sample is an individual. So if you have a sample size of 1, that is the only time when your distribution of sample means will look like your population distribution. At any other time, for a sample size of 2, for example, it starts to change. Your distribution of sample means, your comparison distribution, does not look like your population distribution. Sample size of 3, sample size of 4, sample size of 5. So once again, make sure that you are comparing your sample mean to a distribution of sample means, and you're not making the mistake of comparing your sample mean to a population distribution, a distribution of individuals. You got to be fair with your comparisons. You want to compare means to means. You don't compare samples to individuals. You compare samples to samples. So we need to compare our sample from our experiment to this distribution of sample means. Another illustration, we have the second population distribution. The distribution of sample means for a sample size of 1 is the only time it's going to look the same. As soon as you go to a sample size of 2, sample size of 3, sample size of 4, sample size of 5, that distribution of sample means starts changing its shape. So it no longer is the population distribution. Now once again, you have to remember that you have a sample mean that you need to compare to a distribution. Unfair to compare that to a population distribution. Unfair to compare your sample mean to a distribution of individuals, and that's what the population distribution is. Gotta be fair, compare your sample mean to a distribution of sample means. That is your comparison distribution. All right, and then one more time, population distribution on the left, distribution of sample means on the right. Only time they're the same is when your sample size is 1. As soon as your sample size becomes 2 or more, that distribution of sample means changes. And once again, up to a sample size of 5, you want to make sure that your sample mean from your experiment, from your data, is being compared fairly. And you got to compare sample mean to a distribution of sample means. Hence, this distribution of sample means is your comparison distribution. All right, so once again, central limit theorem for any population that has a mean of mu and a standard deviation of sigma, you find that distribution of sample means, that comparison distribution, and it'll have the same mean as your population. But notice that the spread of these the spread of these distributions gets closer and closer. It squeezes in towards the middle, and that's what this part does. So this distribution of sample means has the same mean as your population, but the standard deviation is different. You got to take the standard deviation of the population and divide it by the square root of the size of your sample. And as you see, it'll approach a normal distribution as the size of your sample approaches infinity. So this is going to be just one more time. I'm going to warn you about skipping this step over here. And partly the reason for that is because you become so practiced taking that single score, that single subject, and comparing it to the population distribution. On top of that, the mean of your distribution of sample means is the same as the mean of your population. So once again, that first step that you have for determining the distribution of sample means is to just go with the population distribution. And I think that lulls students into a false sense of security, saying, oh, I've used the population mean, I haven't done anything with it, let me just grab the population standard deviation. Can't do it. That's the mistake. So once again, look for the need to take that population standard deviation and divide it by the square root of the size of your sample. If you are not dividing by a square root at some point in your hypothesis testing in Chapter 6, you made a mistake. Divide by that square root of the size of your sample. All right, so that's the idea of how to get the distribution of sample means. Pretty straightforward. We're going to go through it one more time just so that it parallels what you're reading in the textbook because they set it up a little bit differently, and I don't want you to get confused on the terminology because it's exactly the same idea, just presented in a slightly different way. So let's go through their 3 rules for determining the characteristics of that distribution of sample means. All right, rule number 1. The mean of the distribution of sample means, the mean of your comparison distribution, is the same as the mean of a population of individuals. So again, this is a very straightforward one. And what they're saying is that your mean of your comparison distribution, and this little extra little m here, is what indicates that it's a distribution of sample means. That's what that subscript is for. So your distribution of sample means, the mean of your distribution of sample means, equals your population mean. So this is the way they write it. I'm not entirely sure why. I find this a little bit confusing myself. But just so you see it the way that it was presented in the textbook, that's why we're doing this. Don't get confused. Your distribution of sample means is the same as your population distribution. That's what this first rule means. And that's a simple one, right? You just grab the population distribution mean, and that is your distribution of sample means. That is your comparison distribution. Rule number 2 is where it gets important. So they got rule number 2a, which talks about the variance of the distribution of sample means. And we're not going to talk too much about this one because we typically don't use variance when we're calculating z-scores. But just for completeness, we have the variance of your distribution of sample means equals the variance of your population divided by the size of your sample. So once again, that is variance, not standard deviation. And remember that variance is the square of standard deviation. Standard deviation is the square root of variance. And that's why you don't see any square roots here, because the population variance divided by the size of the sample equals your variance for your distribution of sample means. But remember, in our z-score formula, we don't use variance. We use standard deviation. So the more important rule is rule 2b, which talks about the standard deviation of that distribution of sample means. The standard deviation of your comparison distribution. And the standard deviation of your comparison distribution is equal to the standard deviation of the population of individuals divided by the square root of the size of the sample. So the standard deviation of your comparison distribution, the standard deviation of your distribution of sample means, you see that little subset m there, that is equal to the standard deviation of your population divided by the square root of the size of your sample. So this is the textbook terminology right there. This is a terminology that we've been using. So once again, don't get confused. the standard deviation of your comparison distribution is equal to the standard deviation of your population divided by the square root of the size of your sample. And once again, make sure that you're taking that square root of the size of your sample, that you're dividing that population standard deviation by the square root of the size of your sample. Otherwise, you've made an error. Otherwise, you've skipped a step. And just to show you how important this standard deviation of your comparison distribution is, just to indicate how important this particular number is, this number not only gets its own symbol, so this sigma with the subscript m, that is the symbol for the standard deviation of the distribution of sample means. That is the symbol for the standard deviation of your comparison distribution. But statisticians used this concept so much that they must have gotten tired in their conversations of saying standard deviation of the comparison distribution, standard deviation of the comparison distribution, standard deviation of the distribution of sample means, standard deviation of the distribution of sample means. That alone got too much for them. Never mind writing it out. So they gave it a term. Just saying it was so cumbersome because they used it so much that they renamed this term, and it's also known as the standard error. And you're going to hear standard error going forward in this course, outside of this course, and just your psychology readings as well. This is what it refers to. It is such an important concept and such an important step that the standard deviation of the distribution of sample means, that standard deviation of your comparison distribution got its own name because it was used so often. It is called the standard error. All right, and then finally we got rule number 3. This one's the easiest one to kind of remember. The shape of your distribution of sample means, the shape of your comparison distribution is approximately normal if either your sample size is 30 or more. So this is kind of fascinating and incredible that regardless of what your population looks like, you could have the wonkiest population distribution ever. It does not matter. Once you get to a sample size of approximately 30 or more, that distribution of sample means, that comparison distribution, will be a normal distribution. So that's one way of ensuring that your distribution is normal. The other way is that if your population distribution is normal, you also have a normal distribution of sample means, regardless of how big your sample is. So this is just something to let us know that we can, in fact, use that appendix to figure out cutoff scores, to figure out where our sample mean is, using the uninormal distribution table, because as soon as you take a sample, once it's 30 or more, you are pretty much guaranteed that your distribution of sample means, your comparison distribution, is a normal distribution. All right, so just to recap and end this, it's going to be a little bit shorter than a typical class, but that's all well and good for a special online class. So just to recap, up until now, you have been comparing your single individual to a population distribution. And that was fair. That was okay because we had a single individual being compared to a distribution of individuals. But now we have a sample. We have a sample distribution. And when we take that sample mean, it is unfair. It is not right to take that sample mean and compare it to a group of a distribution of individuals. All right. Imagine if your own performance was being compared to a group of individuals. Imagine if you were a basketball player and the deciding championship game was going to be their entire team versus you alone, right? That's not fair. Comparing an entire sample of individuals to a particular individual, that's not fair. So we don't compare our sample distribution to our population distribution. We compare a sample distribution to a distribution of samples. That is our comparison distribution. And just to wrap this up, you may have noticed, for those of you that are critically thinking about this and may have noticed this, you'll notice that for this distribution of sample means, you actually need to know what the mean of your population is. right? The mean of your distribution of sample means is the mean of your population distribution. And to figure out the standard deviation for your comparison distribution, the standard deviation of your distribution of sample means, you actually need to know the standard deviation of your population. So the eagle-eyed among you might be saying to yourself, well, wait a second, I thought we were getting to more realistic situations. I thought we were getting to situations where you don't know the population. How are we going to do a distribution of sample means? How are we going to figure out a comparison distribution in that real life situation where we don't know anything about the population? If you notice that, awesome. That's great. That means that you're taking this material and understanding it in a deep way. To those students, I will tell you we will do that next chapter. So the answer to that is coming next chapter. For now, just practice the skills with a slightly easier version where we know the population, we know those parameters, and remember that it is unfair to compare your sample mean to a population distribution of individuals. You have to compare your sample mean to a distribution of sample means, and that means taking your population mean and using it as the mean of your distribution of sample means, but taking your population standard deviation and dividing it by the size of your sample. All right, so that's what I wanted to cover for today. So just a couple of reminders at the end of this session here. So once again, make sure that you're grabbing your 100% pretest points using the MyStatLab study plan. It's just good practice and it'll help you grade as well. And just a reminder, because we are on spring break, the Chapter 6 pretest, that is going to be due after spring break, but by midnight on that Monday. So feel free to watch this video first and, then do the pretest. My little gift to you for helping catch up during this post-snowpocalypse time. But just be sure, get that pretest done, get it in by March 18th by midnight. And then also, because we're not going to be meeting in person, we're not going to have that chance before your homework is due, I've decided to take homework assignment number 9 for Chapter 6, and instead of having it due March 18th, it is now going to be due March 20th. So we will have a chance in class on March 19th for anybody that might have questions about Chapter 6 homework to kind of deal with those and get those taken care of before your homework is actually due. So please make a note of that. The homework assignment is no longer due on March 18th by midnight. It is now due March 20th by midnight. Other than that, we are done for this video. So thank you so much for joining me today for this special online class as we do our last catch-up to account for the missed classes on Snowpocalypse. All right, so I'll see you next time in class.